Hey Team Bio, welcome to your screencast on organic compounds. Okay, so we spent today investigating water, and we're going to move from water to studying organic compounds. Now, we defined organic compounds in last screencast. I hope you remember that organic compounds, they contain either carbon-carbon or carbon-hydrogen covalent bonds. And I don't know if we defined a compound, but a compound is chemically bonding two or more atoms together of different elements. Two or more different elements. So, for example, oxygen, O2, molecular oxygen, this is equal to oxygen bonded to oxygen, like this, and this is not a compound, because it's only composed of one element. However, carbon monoxide, CO, which looks like carbon double bonded to oxygen, like this, this is a compound. Because it has two different elements, carbon and oxygen here. Okay, so organic compounds contain carbon-carbon or carbon-hydrogen covalent bonds. So some examples of inorganic compounds include H2O, which looks like this, as you know from today, or CO2. Oh, it's not bent. Sorry, that's wrong. Erase. Looks like this. Duh. Okay. These are examples of inorganic compounds because they do not contain carbon-carbon or carbon-hydrogen bonds. So this has no carbon in it, so it can't be organic. This CO2 has carbon in it, but no carbon-carbon or carbon-hydrogen bonds. So this is also an example of an inorganic compound, kind of sneaky. Okay, examples of organic compounds. Would include methane, CH4, which looks like this. Or, so this is methane. I guess we should say this is water. This is carbon dioxide. Or glucose, which is C6H12O6. This is glucose. And I'm not going to draw out the structure, but we are going to build glucose later in the year. Okay, so we're going to spend a good amount of time talking about organic compounds. And the reason for that is because all living organisms are made up of the same organic compounds. So we see, if we look at the organic compounds that are in consumers or decomposers or producers, we're going to see the same organic compounds kind of iterated again and again and again in slightly different proportions, but all living things are made up of the same basic building blocks, which is really quite remarkable. Okay, and all living things are using this element carbon to build their complex structures. And in this screencast, we're going to talk about, I'm going to make it a little bigger, why that's the case, why so many living things use carbon as the backbone of all the complex compounds that make them up. Okay, so here's the structure of carbon. It is, when it is uncharged, it is composed of 6 electrons. You know that if you change the electron number, you are going to change the charge. And this is true not just of carbon, but of any atom. So if you remove an electron, you're going to end up with a positive ion. And if you add an electron, you are going to end up with a negative ion. And an ion is just a fancy way of saying a charged atom. So changing the electron number changes the charge. The proton number of carbon is 6. This is also called the atomic number. And it is called the atomic number because if you change the proton number, then you change the element. I guess I should have said electrons, as you know, they have a negative charge. Protons have a positive charge, and electrons are orbiting the outside of the atom. The protons are found in the nucleus, and then neutrons are neutral. They have no charge. And together, the proton number plus the neutron number is equal to the atomic mass, how heavy the element is. So the number of neutrons in carbon, I'm going to say it's approximately 6, because 6 neutrons in the nucleus is the most common form of carbon. But if you change the neutron number, then you do what's called changing the isotope. So, for example, carbon-12, which is the form of carbon that we see here with 6 protons and 6 neutrons, therefore carbon-12. This is the most abundant and stable form of carbon. But if we were to change the number of neutrons in the nucleus to create carbon-14, so to create carbon-14, we keep the proton number the same, because if we were to change the number of protons, we'd actually change the element. But if we add 2 neutrons to the situation, so now there are 8 neutrons, we create carbon-14, and this is a radioactive isotope. The number of neutrons in the nucleus has led to an unstable nucleus that will undergo radioactive decay predictably over time, and that would be the half-life of this radioactive isotope. Okay, so that's just a quick review of the structure of an element and what makes it up. Okay, what makes carbon such a fantastic atom or element to build complex molecules with it? And it actually has to do with the number of electrons in the outer shell. So we call the outer shell of the of any type of element the valence shell. And the number of valence electrons in any shell determines its stability. So the inside shell just requires 2 electrons to be full. But the outer shell requires 8 electrons to be full. And carbon has 4 valence electrons. You can see here, 1, 2, 3, 4. And if this shell were full, all of these electrons would be paired with another electron. So there would be 8 in total. Because carbon only has 4 valence electrons and it wants 8 electrons in its outer shell in order to be full, it will form 4 stable covalent bonds. So this electron, this electron, this electron, and this electron will all form, will all be part of a covalent bond where they join with another atom that has an electron to share as well. So because carbon can form 4 stable covalent bonds, it forms very complex structures. So this property that it has of only having 4 valence electron in the outer shell means that it forms complex structures. So, for example, it can form long branched chains or rings. And that makes it a really fantastic element to build stuff with. Okay, there are 4 major types of organic compounds. We're going to call them the Big 4. And they are carbohydrates, fats and lipids, proteins, and nucleic acids. They're all made up of types of carbon chains or rings, and they all have basic building blocks. If you have one of something, one building block, it is called a monomer. You can kind of think of it as like one Lego piece. If you have 2 building blocks stuck together, this is called a dimer. If you have 3 or more building blocks here, you have what's called a polymer. So we're going to talk about the names and structures of dimers, monomers, and polymers of all these big 4 different types of organic compounds in the weeks ahead. And we're going to build a lot of them. And we're going to talk about the relationship between their structures and the functions that they play in living things. Okay, this is kind of a dry screencast, but an important one. I'll see you all in class on Wednesday.